All right, so this is the Describing Redox Reactions and Balancing Equations lab. We're going to go through 6 redox reactions, and the first one is the reaction of zinc with sulfuric acid. So this is called mossy zinc, and it's just very kind of globular, almost drip-like pieces of zinc metal. We don't need much. I'm just going to take this one chunk right here, drop it into my test tube, and we're going to use a couple of milliliters of 6 molar sulfuric acid. So the dropper, these droppers, some droppers have lines like this one. These are called graduated droppers, and the line at the top is 1 milliliter. So as long as I draw up 2 stemfuls, that's about what I'm going to need. So we see the bubbles forming. Those bubbles are a hydrogen gas. And I'm covering the top of the tube with another test tube. I'm going to try to collect that hydrogen gas because I want to verify that it's hydrogen by running a test. So we're going to let that run and react for a little bit. I don't know if you can hear that. So what I'm going to do is I'm going to light a match. I'm going to lift up the top test tube, and I'm going to hold the match underneath the top test tube. And we'll see what happens. I realize I'm not going to be able to strike a match while I'm holding this, so I'm going to use our clicker. So that popping sound is the characteristic test for hydrogen. It's kind of like a barking sound. So we run this test when we want to verify that indeed hydrogen was produced. Now, because I can see a gas form, that doesn't mean I know exactly what it is. So that's how I verify hydrogen. Reaction 2 is the reaction between sodium iodide and hydrogen peroxide. And we're going to start by measuring or adding about 2 milliliters of sodium iodide. Concentration is 0.1 molar. So there's the sodium iodide. We're going to need some sulfuric acid. Now, when we're using concentrated acids like sulfuric acid, one thing to point out is when you use a dropper, you need to make sure you always set the dropper down on paper towel. And the reason for this is because it's so concentrated that if you were to just put it down on the lab bench, somebody might not know it's there, put their hand down on it or put their paper down on it and get a nasty surprise. So with concentrated acids and bases, the discipline is to always just take a paper towel and deliberately set it down, and that's going to be where you set down your droppers. Because in these kinds of labs, more than likely you'll be picking them up and putting them down over and over again. You want to have a constant place to do that. So I'm going to need some sulfuric acid. I'm going to use about 1 milliliter. These redox reactions often need a very acidic or very basic environment to to react. And now we're going to need some hydrogen peroxide, commercial grade, just 3% from the drugstore. So you see the iodide solution was clear initially, and by creating an acidic redox environment and adding the hydrogen peroxide, we now have this kind of orange color. So one way to verify what we have made in here is to add a nonpolar layer, like a layer of hexane. And if there's any nonpolar molecules, they'll dissolve in the hexane layer. Now the hexane is less dense than water, so when we do that, we'll get a separation based on density, and we'll be able to tell the top layer is the less dense layer. You see we get a pink top there, a magenta top. The magenta color is characteristic of diatomic iodine. So diatomic iodine is a product here in this reaction, and it's being dissolved in the hexane layer on the top, which is less dense. Reaction 3 is the reaction with potassium permanganate with hydrogen peroxide. So we'll start by adding our sulfuric acid. Next, we're going to add 2 milliliters of hydrogen peroxide. And we're going to add 1 milliliter of potassium permanganate. Note its initial color, it's a very, very deep purple. And then we're going to stopper this and shake it up. Notice the lightening of the color. And we're getting clearer and clearer solution. Probably needs to sit for a little bit longer, but this will eventually end up almost completely clear. So we went from a deep purple to a clear solution. Reaction 4 is the decomposition of hydrogen peroxide. So we're going to start by adding our hydrogen peroxide to a test tube. And we're going to use manganese dioxide. Now, manganese dioxide is what we call a catalyst. And a catalyst, by definition, speeds up the reaction, but is not itself a reactant. It's not consumed in the reaction. So this MnO2 that you're seeing me add is not to be used in the balanced reaction. We get lots of bubbling, lots of fizzing. Now what we're getting is oxygen gas being released and water. Now you would think, based on the formula of hydrogen peroxide, that you get hydrogen and oxygen, because that seems like it would make sense if H2O2 were to break up, but actually that's not the case. The products are not hydrogen, it's oxygen and water. Reaction 5 is the reaction between potassium dichromate and sodium sulfite. So we're going to start off by acidifying our test tube with sulfuric acid again, same as before. And now we're going to add our potassium dichromate, which is a very vibrant orange, almost like a neon orange. Add about 1 milliliter of it. Then we're going to add our sodium sulfite solution. And here we get this kind of olive green color. This green color represents the chromium ion when it's in an acid solution. So hence verification that chromium 3 was formed. Reaction 6 is the reaction of granular aluminum, granular as in just grains of aluminum, with water in a basic environment. So I'm just going to go ahead and add some of these aluminum granules. Little small grain pebbles. And I'm going to add some water from a wash bottle, about 2 milliliters or so. And then I'm going to add sodium hydroxide concentrated to give it a basic redox environment. I'm going to cover this with a test tube. Is not as fast of a reaction as it is with the metals and acids, but hopefully you can see the bubbles forming. And so the bubbles are the formation of hydrogen gas, as well as the product. The product is called tetrahydroaluminate. So I'm going to collect gas here for a little bit, and then we're going to run the hydrogen test. Although I may pause the video here because I think this is going to take longer than the previous one. Okay, we're going to ignite the hydrogen gas that we've been collecting. and we didn't get a pop. That's sometimes it happens actually fairly often. We just don't get enough hydrogen gas, but it definitely was hydrogen gas being formed. I guess you'll just have to take my word for it.